Every aquifer is unique. The properties of these vast underground systems, how much water they hold, how quickly water is recharged, how vulnerable their water is to contamination, and how expensive it is to pump water out of them, are all determined by varied and complex geologic processes that play out over many millions of years and throughout many thousands of cubic feet of rock. The job of the hydrogeologist is to discover these properties, but because aquifers are deep underground, they're rarely observed directly. In karst systems, however, in landscapes made of easily dissolved rock, caves can offer a rare window into the subsurface. I'm Logan Schmidt, and this is The Recharge Zone, podcast from the Edwards Aquifer Authority in San Antonio, Texas, where we explore the biggest concepts in Central Texas hydrogeology. In this episode, I talked to hydrogeologist and karst expert, Dr. George Veni. I asked him, what can caves teach us about the groundwater resources in Central Texas? And how can this knowledge help us manage, enhance, and protect the Edwards Aquifer? George studies caves to understand groundwater supply and contamination. He has also worked extensively on cave biology, endangered species, archaeology, and paleontology. George is the principal investigator for George Veni and Associates, an environmental consulting firm specializing in multidisciplinary research and management of cave and karst systems. He has also served as executive director of the U.S. National Cave and Karst Research Institute. George, it's so nice to speak with you. Thank you for joining us.
Great to be here. Thank you.
So in the intro, I mentioned karst a couple times. It came up. It's part of the title. If anyone looks up your name, it's karst will come up. And I thought we'd start by defining karst, but I kind of wanted to frame it in a kind of a whimsical way. I wanted to imagine like a hypothetical world where no one had ever been to Texas. And I was wondering how would a team of geologists that were transported to maybe San Marcos Springs or Comal Springs, how would they go about understanding where that water was coming from?
Oh, well, there's a lot of things to unpack there. First, let's define karst.
Okay, let's
get that out of the way. Karst comes from the word kras. It's a region, and most of which is in modern-day Slovenia and a little bit of the northeast corner of Italy. During the years of the Austro-Hungarian Empire, the word kras was Germanicized into karst, a good German-sounding word, and it defines a type of landscape. Much like mountains and beaches are landscapes, karst is a type of landscape. Mm-hmm. With a beach, you can close your eyes and you can imagine waves coming in and out, moving sand and gravel around. You can visualize how a beach forms. And most landscapes are formed by those mechanical processes, water moving grains, cutting deeply into the earth. With karst, it's not mechanical, but it's chemical. Karst is formed by dissolving away the rock. And so a karst landscape usually occurs within certain types of rocks. Limestone is the most common, and that's primarily what we have here in the Edwards. Dolomite, which is related to limestone. In dry climates, you also have marble, but in dry climates you also have gypsum and halite, which is rock salt in super dry climates. All of these things dissolve fairly readily, and so water moves into these cracks, dissolves them, makes them a little bit bigger. Because they're bigger, they can take more water, so more water goes in, and they become even larger. The process self-accelerates. If that hole in the ground becomes big enough for a person to enter, we call it a cave. I'll also be using the term conduit. Mm-hmm. I know I'm just going to do it automatically, mm-hmm. So let's explain that as well. A conduit is a cave that we can't fit into. So a cave is a humanly enterable conduit. Hydrologically, they function the same way in terms of how water moves through them, the chemistry, their ability or lack thereof to filter contaminants. They both move sediments. They will both house aquatic animals that live underground, live in the aquifers. So I'll use the terms sometimes interchangeably, but those are the key things.
I really like, and I've never had karst explained with the perspective of, I like how you emphasized the processes that are social, like you said, in a beach, we can imagine how a beach forms. There's oceans, there's sand there because rivers deposited grains of that size, and there's waves, and you can kind of put together a story. I have a little bit of a background, or I'm interested in geomorphology, so I really like imagining how landscapes form. But I love the idea of, okay, if I know if I'm in a karst region, it automatically implies that certain processes are happening, and you can imagine what, and then that helps you tell a story about what features exist. And also, like, the clarification, but the distinction between conduit and caves sort of is an anthropogenic one, in that they're not really maybe like process-based difference, other than a cave a person can go into, but conduits kind of behave similarly. So I really appreciate that. So how would you, if you were transported to a random landscape, how would you go about deciding whether or not it was a karst landscape?
Karst is really difficult for people to grasp, to understand, in part because it's a more abstract process, this dissolution process that happens over, thousands of years. Let's watch the rock dissolve, and you sit there and nothing's happening. So that's kind of abstract. But the other thing that's a challenge is that visually, if you go to different karst landscapes around the world, they can look dramatically different. There's towers in China, for example, Southeast Asia, that are created, they're karst features, where the rock has rapidly dissolved downward and left these towers standing up, 100, 200, or 300 meters up into the, pointing toward the sky. In Texas here, we have a very topographically subdued karst. Some parts of the world, you have sinkholes that are 100 meters or more in diameter. Here, I get excited if I see something 1 meter in diameter. So you drive through this, you don't see anything immediately that jumps out at you and say, aha, this is karst, unless you're a geologist and you recognize, this is limestone and it's a soluble rock. And when I talk about solubility, some research I did as part of my dissertation years ago, the rock in this area is being dissolved on average of 1 inch per 1,000 years. So come back 1,000 years from now, and overall, the landscape will be 1 inch lower in elevation. So again, it's a slow process, but geologic time, that's pretty quick. So in this area, again, the karst is topographically subdued. You really don't see anything. Now, if you go past a road cut, which is cutting into the rock, you might see some little cave-like features. That might tell you you're in a karst landscape. If you go to the San Marcos or Comal Springs, you might get a hint because you've got very large springs. The largest springs in the world are in karst because water's moving through these large channels that we call caves and conduits, and so they can discharge the highest volume of water. But you really don't see them at those springs. But if you come here today to San Antonio and you go behind Incarnate Word University, you'll find what they call the Blue Hole. Its proper name is the San Antonio Spring. It seems half of the springs of the world are called blue holes, but it's dry. Water levels are low, and you'll see a hole going down. You go to San Pedro Park Spring. It's a hole. It's too small to get into, but it goes off into this short little cliff in a pool, and so you get the sense if you're looking for cave-like features, which are typical features of karst. Sinkholes are typical features that you'd look for. A sinkhole being a closed depression, so if water flows in, it can't flow out overland. It has to go downward. Some parts of there's two types of sinkholes, two major types. One is what we call a solutionally formed sinkhole. The rock is being dissolved downward into this bowl-shaped feature, and that's what we have here. In other parts of the world, they have collapse sinkholes, where the ground is collapsed downward. We do have those here. They're less common, and ours here are formed in bedrock, where there is an underlying cave and the roof fell in. Whereas the ones that you see in the news, like in Florida, places like that, those are where the soil has washed down into an underlying cave and created a soil cave above the rock, and then the soil collapses in. But we don't really have to worry about that type here. So the sinkholes we have are fewer and happen less frequently. But those are the sorts of things I would look for to tell me if I'm in a karst area or not.
It's, you're kind of nerd sniping me with the 1,000 years per 1 inch of dissolution. It's really satisfying to have a number like that to put on rates of, I guess that's salt, chemical weathering. That's how fast in, I guess, Central Texas, roughly, our limestone dissolves. It's very evocative. What is it about limestone and maybe even gypsum or dolomite that makes them soluble, quote unquote, at least on geologic timescales, versus other kinds of rocks?
You're right. I mean, anything can be dissolved. It just depends how long you want to wait. Mm-hmm. And some things won't dissolve, within millions or barely will dissolve in billions of years. Mm-hmm. But limestone, it's just its basic chemical makeup, calcium carbonate. When it comes in contact with, not with water per se, the calcite crystal is the primary mineral in limestone. And you can take a piece of calcite and drop it into absolutely pure water, and it will sit there and nothing will happen. Mm-hmm. But what happens with karst and with limestone is that as rain's falling from the sky, it picks up carbon dioxide that's in the atmosphere. And then as that water moves into the soil, it picks up more carbon dioxide that plants are releasing through their roots into the soil. And that carbon dioxide with the water forms a weak carbonic acid. It's nothing that burns us. I mean, we've all dug around in our gardens and got moisture on our hands, and we didn't dry up and burn up or anything. But over thousands of years, it will slowly dissolve away the rock. And so it's just prone to that. Gypsum is far more soluble. Gypsum will dissolve in pure water. Halite, rock salt. I mean, we've all put, salt in water, and that just disappears, dissolves pretty much instantly. It's just the chemical structure of those minerals, of those rocks, that allow them to dissolve.
I have a question. Have you ever heard of a study, or I guess a thought experiment? You have two identical rocks, or maybe regions with the same rocks, and in one region, you have maybe more karstification, more solubility than other. Could you use the amount of karstification, amount of conduits and caves, to sort of as a proxy to back out information about, I don't know, the climate or the soil or the microbes? It seems like because you're saying that water itself isn't going to dissolve calcite necessarily, but it's water interacting with the environment that kind of drives how much chemical weathering it can do.
Yeah, variations in karstification, let's say cave development, sinkhole development, and so forth, will vary. It depends because, for example, with the Edwards limestone, you've got 8 subunits of rock within the Edwards limestone. And they have different characteristics. Some dissolve more easily than others. You also need to think about, is this rock fractured? We live in the Balcones fault zone. Now, most caves are not formed along faults. This is a common misconception that people think all caves are formed along faults. No, but along each fault you have many fractures called joints. A fault is where movement has occurred along the break. A joint is like a crack in your windshield. There's been no movement. And so most caves will form along joints that are associated with faults. And so if you get further and further away from a fault, less fracturing, that will affect the amount of cave development. We're looking at factors such as, was there a stream over this location in the past, and maybe the stream has moved somewhere else. So that's another factor. There are different types of karst. Hypogenic karst, for example. Most karst that we classically think about, the way I described, is water moving down into the earth, moving into the aquifer, and then flowing out of a spring at the bottom. But there's also hypogenic karst, where water goes into the earth at some far distant location and then rises up in this location. And so if that was an ancient process that we don't see anymore on the surface, it could still affect surface development of karst. So there's many factors in terms of why something's happening here but not there. And I started this as a cave explorer. I was crawling through the geology, developed an interest, and ended up where I am now. But initially, as that cave explorer, I was doing the Star Trek thing to go where no one had gone before. My cave is going to be bigger than your cave, But also just to see that map grow. Where is the cave and so forth. But now as a hydrogeologist, I'm looking at a cave map and I'm looking at the plumbing structure of the aquifer. I'm understanding how this aquifer formed, at least at the time that the cave formed. Maybe the cave is completely dry now, and many of them are because they're way above the modern water level. But I know what happened in the past, which helps me understand what's happening in parts of the aquifer that I can't physically get into. So these all connect in many ways.
There's a lot you touched on right there that I want to ask about, including faulting. But maybe right now, could you break down a little bit, how are karst aquifers different than other kinds of aquifers?
The most common type of aquifer, the one that's most widely taught, is the simplest type of aquifer. It's what we call a porous media aquifer. Sandstone, the Carrizo aquifer on the south and east sides of town is a sandstone aquifer, fabulous aquifer. Water moves and is stored through and between the grains of sand. It's a great filter medium. It's one of the earliest ways of filtering water for drinking. You get a tube, you fill it with sand, put water in the high end, and by the time it comes out the other end, it's pretty clean, much safer for drinking. With those aquifers, water moves in a very uniform direction. You can develop beautiful models to predict how that water is going to flow. It's moving slowly at the rate of, let's say, meters per year or tens of meters per year, depending on the aquifer that you're dealing with and where you're at. You have fracture aquifers. If you go up to Enchanted Rock, you've got that big chunk of granite sitting there. Water doesn't flow through that rock, at least not in any appreciable amount, but water is moving through the fractures in the rock. That's a different type of system. It's a bit more complex. Karst is far more complex. You have microscopic openings, you've got fractures, and you've got these solutional openings. I've often give the example of how I've stood in many cave streams and the water flowing around my body may have entered the ground as recharge maybe a few minutes ago, an hour, a day, a few days ago, a month ago. Meanwhile, the water dripping on my head is coming out of these tight fractures, the microscopic pore spaces of the rock, and that water may have recharged the aquifer tens of thousands of years ago. So it's just this incredibly complicated system. These are the most complex type of aquifers on the planet. And here in the Edwards, I think of it as perhaps the most complicated aquifer in the world because we've got, as I mentioned earlier, these different sections of rock within the Edwards. Mm-hmm. You've got the faulting that jumbles it all up, raising it here, lowering it there. And something we're starting to realize people like myself who've been climbing through the geology for a long time are seeing that the Glenrose Formation below the Edwards for many years was considered the impermeable base, the bottom of the Edwards, but no, there's caves formed in the Glenrose and they're connected hydrologically to the Edwards. Natural Bridge Caverns, which advertises itself justifiably as Texas' largest cave in terms of volume, most of that cave is formed in the Glenrose. And it ends up recharging the Edwards. It's a complicated system. The longest cave here in Bexar County is in the Austin Chalk, Robber Baron Cave. It was a show cave in the 1920s, now owned and managed by the Texas Cave Management Association. It formed as an early spring for the Edwards Aquifer. Mm. And with time, as the landscape has cut and lowered deeper and deeper, now the springs are down, as I said, along Almas Creek, behind Incarnate Word. But at one time, over 1 million years ago, I remember it well, it was way up, up on a hill, near Nacogdoches Road. So these things change and evolve with time. And these are just a hint of some of the complexity that we deal with.
There's, up top we talked about karst. It's kind of a funny word of Slovenian origin, but then became Germanicized. And I was thinking of mnemonics. The one that occurred to me is like karst chemistry, or karst is evolved in chemical weathering. Now I'm thinking karst so it goes with complexity. You just beautifully described a lot of ways that caves offer an opportunity to grapple with the complexity of karst aquifers. But could we kind of talk about that a little bit more? What do caves teach us about karst aquifers? What can we learn about them? You kind of already mentioned that you can see where springs used to be before erosion has lowered the land. You've talked about hydrostratigraphy, but in your view, what are the advantages of having caves as a hydrogeologist?
Well, first I need to go back to wordplay with karst. When I first met the lovely woman who became my wife, I confused her, and I still confuse her to this day, 35 years later. 37 years, we've been married 35. But anyway, because she knew I was very much into caves, but I was also very much into car stereos. And she couldn't understand this connection between caves and car stereos until she finally, embarrassed, asked. And I said, no, karst areas, not car stereos. But anyway, caves. I touched on this before a little bit. Caves are the basic plumbing structure of the aquifer. Going into a cave, I can see that plumbing structure. I can visualize what's happening in the smaller part I can't get into. Or maybe it's blocked off because sediment filled the cave, whatever. I can figure out what's happening in other parts of the system. Karst aquifers are the most vulnerable to contamination. Because as I said, remember I was standing in that cave stream. Well, I'm a giant contaminant. If I'm not being filtered out of swimming in your aquifer, and I have been swimming in the Edwards Aquifer, I don't taste very good, by the way. Then what about oils, grease, heavy metals, chemicals, pesticides, herbicides, bacteria, things that are tinier, much tinier than me? Those things are not being filtered out either. Karst aquifers are the only aquifers that can be contaminated by solid waste. I've been down in aquifers, in cave streams. Cave streams are part of the aquifer. Pulling out car batteries and bodies and other trash that's been dumped in there. So these are some of the things that some of the vulnerabilities of caves. But there's so much that they teach us. While I am a geologist, a hydrogeologist, I've worked a lot, as you mentioned in the intro, with biologists. The biology teaches me a lot about the aquifer. For example, Jean Kretche, a former student of mine, Dr. Kretche now, she did her dissertation at UT, and she was looking at a certain aquatic animal that lives in the aquifers, the karst aquifers of Texas, and using the genetics of that animal to understand where aquifers were connected and not connected in ways that our models and other tools don't tell us right now. You mentioned climate change. Scientists around the world are starting to recognize that caves are the most valuable source and certainly the most diverse source of paleoclimatic data. Because if you're trying to predict how climate's going to change in the future, you need to look back to what it was like in the past. And so you go, for example, I mentioned natural bridge caverns. You go into natural bridge, you see those pretty crystal things, stalactites, stalagmites, and so forth. Yeah, they're pretty to look at, but those crystals have microscopic bubbles of oxygen in them. And by testing the crystal itself, we know how old that crystal is, and then testing that air inside those bubbles will tell us what oxygen was like, how much CO2 was in the atmosphere, what the air content was at that time, 100,000, 200,000 or more years ago. Looking at other isotopes in those crystals, we can understand what the temperature was like here. Going into the sediments in the cave, we can look pollen, spores, bones, find out what plants and animal communities were here. Some of us will joke about how thin the soil is. You get 6 inches of soil, and it's like, woohoo, yeah, it's really deep here, especially on the north side of San Antonio. But how many people know that during the Ice Age, 10, 15,000 years ago and older, we actually had a very thick soil cover here. And we know that from caves because as the Ice Age ended, we came into this erosional cycle, and the soils began to slowly wash off. A lot of those ended up in caves. And it's recorded. There's tremendous data being recorded. John Moretti just last week defended his PhD dissertation looking at bones from some of the caves in this area, but especially up at Interspace Cavern, and finding fabulous information about these past climates. So there's so much. There's such a wealth of information. It used to be that many geologists would look at caves and say, well, yeah, it's just kind of a quaint curiosity thing. They didn't really understand the value. My PhD advisor would be able to tell you about the days where if he submitted a scientific paper to a scientific journal for publication and it had that vulgar 4-letter word cave in the title, it was an automatic rejection. It wasn't considered serious science. When I was an undergraduate student here in San Antonio, I got my bachelor's at UTSA. I had professors at UTSA. I had people, the predecessor organization to the Edwards Aquifer Authority, the Edwards Underground Water District. I had people at the various state water agencies, the U.S. Geological Survey, all tell me that there's no karst here in Texas. There's caves, there's sinkholes. If I want karst, I need to go to Mammoth Cave in Kentucky. They didn't understand what this was. They didn't understand what karst is. We've made a lot of progress here. People are starting to understand karst. Not everyone fully understands all the applications, the implications either. But we've made a lot of progress. I would have loved to see it go faster, but I'm glad to see how far we've come. So caves are an integral part of the aquifer. That's why the Edwards is so prolific, because it has these big holes in the ground. And most of them we don't go into because they're filled with water and they're way below the surface, but they're there. We know they're there because we drill into them. The largest free-flowing well in the world, the Catfish Farm well, drilled, 1990, 91? It's because they went down a long way and hit a cave that was about 8 feet tall. We don't know how wide it was, but and then water shot 30 feet into the sky, under such incredible pressure. So we know that the caves are there. The aquifer behaves in a certain way. I can feel your pulse. I don't need to see your heart beating to know that your heart's beating by feeling your pulse. And so caves are telling us how this aquifer is, what it is. There's so much about it.
Wow. So you mentioned some things that I hadn't. So let me see if I understand. Caves, they kind of serve as repositories, or they contain records that you can get information about all sorts of things like the climate. I love the idea of understanding what soil was like in the past, because it's saved in caves where all the rest of the soil might have been washed away into the Gulf of Mexico, but maybe caves are holding onto some soil. But what about mapping? Like, do caves provide? Do people go into caves and look at the stratigraphy of the rocks? Do they provide windows? Because I know geologists will look at road cuts to understand what kind of rocks are in places. Maybe they'll look at cores from wells, maybe canyons that have been carved by rivers. Are caves a useful source for that sort of information?
Yes, they are. Your typical caver, cave explorer, is not a geologist, but they're the Lewis and Clarks. They're out there doing the basic mapping, exploring the terrain, where then the scientists can come in, the managers can then follow to do the research. So the Nullarbor Plateau, this vast karst plain in south central Australia, was mapped many years ago on a cave-to-cave basis, that's stratigraphy, because they just go into the cave and map the layers. It's flat. It's just this flat plateau for vast distances. And so you go into the caves and you see the rock strata there. Why drill a hole? That costs money. I can just go into the cave and map the strata, map faults, whatever. And so they provide that information. But your typical caver will not do that. They're not trained. They can be doctors, teachers, accountants. I've had cavers who were you take take your pick. There are, people who are Hell's Angels type bikers all the way to priests, everything in between, all skill levels, all education levels, mechanics to PhDs, everyone can do it. They have this passion to explore, to see what's around the corner. And the way you do that is to map it. Mm-hmm. You don't know where you've been unless you've created the map. So you go in, you make the measurements, distance, azimuth, your direction, vertical direction up and down, and draw a sketch. Now that we've got high-tech things like LiDAR and other methods, those are developing to be more useful underground, but they're not super useful in some caves, but it's getting there.
I have to ask because I'm curious. I'm a little surprised at the sort of, sounds like prejudice maybe is a word people had against caves. It's interesting to me that caves would be a 4-letter word in academia. And I wonder, is some of that coming from the fact that non-academics participate in caving? Do you think, what's your take? Why do you think caves had such a bad rap early on?
You're right. I think that's part of it. It was, I know early in my career, some people, some academics considered me a hobbyist because I had someone, he didn't stay on my PhD committee very long, thankfully. And he says, "Oh, you're just out there having fun, going into caves." And his specialty was modern carbonate depositional environments. And I retorted back to him and said, "Yeah, I know. You're just absolutely miserable on the beaches of Bonaire studying your modern environments, carbonate environments. Just because you enjoy your work, that doesn't make it invalid." It was just utter nonsense. But again, those attitudes have largely disappeared. And I'm so grateful for that. So, but there was a certain prejudice, but there's so many prejudices and superstitions associated with caves, and I think part of it, though, especially with geologists, if you go back into the late 1800s, there are some U.S. Geological Survey reports that deal with caves in a realistic fashion for the knowledge they had at the time, but most of these curiosities because they didn't understand them. As they tried to fit caves into the hydrologic models that were available in the 30s, the 40s, the 50s, the 60s, they weren't fitting real well. And so it's just easier to dismiss them. But then after World War II, we had an organization called the National Speleological Society that was created, caves.org. Very easy to find. If anybody's interested in exploring caves, go to caves.org. You can find the Bear Grotto, which is the caving club here in San Antonio, and other grottos. We call our chapters, our clubs, grottos around the country. But people came out after the war and really started going out, exploring caves, and creating these maps that were filled with data. Mm-hmm. And then people started going in, doing geological studies, biological studies, and so forth. And with real data, people like my PhD advisor were able then to present this data and present it in a scientific fashion that started showing, there's something real here. These aren't just quirks of geology. These are here for a reason. Just because you don't understand that reason doesn't mean we should ignore them. And so now we understand them more and more. Mm-hmm. They're incredibly complex. And when I talked about, for example, the Carrizo Aquifer, we can model that. Modeling a Karst aquifer is incredibly difficult. I have mixed feelings about the models. I think that at a big scale, looking at overall function of a Karst aquifer with a model, they work really well. But as you get into the details, you're getting into a lot of complexities that the current models aren't set up to deal with yet. But as the computing technology is getting better, as the information we're gathering is getting better, we can plug this information into the model. That's making the models better. So it's exciting. It's to watch that. It's exciting to see that people are now using the Karst word, the K word, About 15 years ago or so, a group of us created within the Geological Society of America a Karst division, a group to focus on karst. And now we've got several sessions, and the convention, the Geological Society of America convention, will be here in San Antonio this year in October. And now karst is being spoken. The word is being spoken. Again, many people aren't as familiar with the word. They're not getting the level of education that they need, but it's so much better than it once was. We've got a karst expert, at UTSA, whereas I didn't have a karst expert when I was a student there, Dr. Yongli Gao from China. And there's fabulous karst in China, and he's an excellent scientist. We've got excellent karst scientists at many universities here in Texas now.
Okay, so we talked about something I'd like to drill down to a little bit is, so we talked about karst versus porous media aquifers, and you very wonderfully explained how karst aquifers are more complex because for a variety of reasons, but a big one is that they have conduits that are solutionally created, that are like essentially large pores that are not spatially uniform, and they're hard to predict where they are. But I want to be clear. So I think a lot of people, not only people not think about karst a lot, I think a lot of lay people might not even think about aquifers a lot. And I think maybe when I talk to a layperson about groundwater, I wonder what they're imagining. And I think sometimes they might be imagining caves. But I just want to be clear that most aquifers, like you said, aren't caves. And if they're not caves, then they're simpler in a lot of ways, because you can make assumptions about how their properties vary in space, and you might be right. Whereas that's not necessarily true with karst. Would you agree? Does that make sense?
Yeah, I was told that in my introductory geology class at UTSA that there are no underground streams in aquifers. And I went to the professor afterwards and said, yeah, I've been exploring them and swimming through them. You mean there's no underground streams? And he says, well, I'm just simplifying for the class because really hydrologically they're not that important. He said, think about it. I mean, the cave occupies such a small volume of the total mass of rock. And it's like, okay, I mean, this is my first freshman class. What do I know? I didn't argue with him, but some years later, about 25 years ago, some friends of mine brilliant scientists. They did some detailed work looking at some very diverse karst aquifers around the world, and they found very, very similar results from these very different types of aquifers. What they found was that my professor was right to a point. At any given point in time, there's not much water stored in the caves and conduits, about 60%, 6.0%. But if you look at how much water moves through the aquifer over time, 99% is moving through the conduits, through the caves and conduits. So that's where the action is happening. The water that's in the fractures, the water that's in the tight pores within the limestone, it's there, it's moving, but essentially it's sitting there. It's moving very slowly. Most of the action, most of the groundwater movement through the aquifer is happening through the caves and conduits. So we can't ignore those. We can't ignore the fractures in the other parts of the aquifer. We need to study and appreciate the whole picture. But where things are really happening are the conduits and caves.
So I want to emphasize that 6%, let's say you have a karst aquifer, generic karst aquifer, you might expect something like 6% of the total water is in conduits, but 99% of the flow is in the conduits.
Is through them. Think about it this way. Okay. Let's say we're sitting in this building here. There's a repeated biblical flood. And now we're 100 meters underwater. And assuming the windows don't shatter and whatever, we can expect that some water, because of the force of the pressure, will start to beat up on the walls, working its way through the sheetrock and everything else. And it's like, okay, yeah, that's all right. It's just kind of like sweat, and I'm not going to worry about that. Then you'd look at the doors, and you see around the edges of the door, water seeping a bit more quickly. That's kind of like fractures, and you'd be a little bit more concerned about that. But if I came up to those walls and punched a hole through it, a fist-sized hole, where are you going to run and start plugging the leak? That fist-sized hole. So even though by size it occupies a relatively small space among all the walls of this building, that's where the rush of water is going to flood in and flood the building. And so that's a way of thinking about how, the larger the hole, the more water can move more rapidly through it.
That reminds me of in our house. We live in me and my wife live in San Antonio, and it gets very hot in the summers. And the house is old, and so it's not very well insulated. And we had an old door that didn't fit properly in the frame, and it was the same thing. All of our cold air was going out through the cracks around the door. So there's maybe an analogy with heat transport and water transport in that way.
Exactly.
So can we talk about visualizing the Edwards Aquifer or a Karst Aquifer? If it was a porous media aquifer, you might just imagine a big layer of rock, maybe like, and if you're you think of it like a cake or something, it's got pores and there's water in it, and you can suck the water out. But do you have a picture that you could paint for the gross structure of a karst aquifer? Does it look like a drainage channel? Does it look like veins in the human body, or a tree, or something like that, or what, or is it too complicated to even make any sort of statement like how to visualize it?
Simplistically, karst aquifers look like a stream system.
Okay.
They are confluent or contributory systems where you have little streamlets that join together to form a bigger streamlet, and join together to form a stream, to form a major channel, and so forth. And so, if you imagine a branching structure, somewhat like a tree, you've got that sort of structure, but over very large distances, going from San Marcos all the way out to Bracketville. But then it's also three-dimensional, because when we're talking about the stream, we're just kind of thinking about looking down from the
2D.
sky and in that two-dimensional image.
Right.
But in this case, we've got water going vertically downward,
right,
and then it doesn't go straight down to the water table, but may offset and go horizontally, and then drop down again. So it's super, super complicated.
Right.
One way of maybe thinking about it, it's not quite a great analogy, but have you ever seen a tree that's been knocked over by a strong wind?
Sure.
And it's laying flat on the ground, and so you can see the branches coming together on the ground, but then the surviving branches grow straight up toward the sky.
Yes.
In a way, that's kind of like how the aquifer works. And so the ones going straight up are the ones recharging water downward, and then moving along the trunk passages. But far more complicated.
I love that picture, and I really like that. So maybe you could imagine you put a tree like that, you take a tree and you put it in a big box, and then take a cast of it, and take the tree out. And so now what's left behind is the void space left by the cast of the tree, and maybe whatever material you use to make the cast is a little bit porous. Then maybe you have sort of an idea of what a karst aquifer is like, except in the Edwards, and I'd like to talk about this now, we also have faulting. You mentioned faulting is when rocks move relative to one another. I believe in the case of the Edwards Aquifer that we have what are called normal faults because of, I believe, the sediment building up in the Gulf of Mexico and causing the crust essentially to sink. So then we have faults sort of superimposed on this three-dimensional branching structure. Can you talk about, do you think about faults when it comes to hydrogeology? Is it important to think about faulting? And do caves help us understand how faults interact with groundwater systems?
A friend of mine, Ernst Casting, wrote a paper, I think it was 1978, 79, about the influence of faults on groundwater flow in caves. And he used natural bridge caverns as one of his examples. And so it's now called the Hidden Wonders Tour. If I'm still familiar with the old names of the passages before it was open to the public. But in that part of the cave, you're walking down the cave, and then suddenly it makes a sharp turn. And you look and you say, oh, yeah, there's a fault. And so the fault is guiding the cave development. And so that's a positive influence on groundwater flow. And then eventually the cave leaves the fault and continues on its merry way. And then if you're paying really close attention, you'll see another fault that you just walk through that's had no influence on the cave. So there's neutral effect on caves. And then you keep going until you reach the end of the passage, and it ends in a big fault. And so there's a negative influence on cave development. So you can have all three occur. It depends on the type of fault, depends on how much rock is moved from one side to the other. So where the cave ends now, it's because you had a less soluble limestone opposite the section of limestone that you're in. Mm-hmm. And so one part was dissolved easily, and this other part wasn't. And so the cave really doesn't end. It ends as far as human exploration is concerned, but the water finds a way around and that barrier. But yeah, faults can have positive, negative, or neutral influences on caves.
So sort of a whole spectrum of effects. And it sounds like you had examples from the full spectrum in one single cave. Is that what you're saying?
Yeah. When I do an evaluation of a cave, I'm looking at all the fractures, whether they're joints, faults, their orientation, the types they are. I'm looking at sediments. I'm looking at flow features on the wall, how the wall is sculpted by water. I'm looking at bones. I'm looking at cultural remains, if there are any. Usually not, but sometimes there are. I'm looking at the cave fauna. I'm looking at the stalactites, the stalagmites, how they are formed, how they are not formed. I'm feeling for airflow in the cave because that's telling me something. I'm feeling for air quality because some caves in this area have at least seasonally high levels of carbon dioxide in them. So these are just a few of the things, not even talking about the water yet.
Right.
So these are all sorts of things I'm looking at and piecing putting pieces of the puzzle together. And it can be really, really informative if you understand an area quite well. I worked on a project, groundwater contamination project. I'll leave the names out of it. But folks, some consultants who weren't Karst people came in and they said, okay, they put in some monitoring wells near the contamination site. And I was asked for my input, and I said, let's go 500 meters, a quarter of a mile in this direction, and put a well in. They're saying, you're crazy. That's way too far. So I said, let's go this way. And I walked on the ground, and I said, right here. Drill a well right here. And they started to mark a spot just a few feet away from me. I said, damn it, not over there, right here. You're going to go down 14 meters. You're going to hit a cave that's 1 meter high, and you're going to have your highest contaminant levels. And they did that, and that's exactly what they found. And it's not that I'm brilliant. It's not that I'm psychic. It's just that I've been paying attention. I've been studying that area for a long time. And so I know all those details. You put them together, and you can see the puzzle, come to you. You take me to someplace else, I wouldn't be able to do that because I don't know it as well. But in that case, I was able to, and then I did it again. They were surprised at that. I said, now let's go a mile further in this direction, and we did the same thing. But again, it's not a matter of brilliance on my part, just knowing the details.
And I think that speaks back to this idea of enjoying what you do because, again, like if you were being forced to crawl through caves, if someone was forcing someone else to crawl through caves, it would be horrible and you would not pay attention. But if you enjoy doing it, I had a professor at UT Austin that would say that the best geologist is the one that's seen the most rocks. And then you would say, it's not entirely true, but there's a lot of truth to it. And it kind of sounds like, that always resonated with me. And I feel like it's similar with when it comes to Karst hydrogeology, probably it's not entirely true, but there's a lot of truth to the fact that probably the hydrogeologist that's been in the most caves probably is got a lot of advantages to understanding how things work.
Well, we often say that an outstanding geologist is outstanding in the field.
Right.
Yeah. So, but yeah, it's true. The more you see in any field, then the more informed you are to make good decisions and good predictions of what might happen. They may not always be perfect. Nothing ever is. But the odds are that you're going to get it right more often.
So San Antonio, the city of San Antonio engages in a program, the Edwards Aquifer Protection Program, where they purchase land to protect it from development. Could you talk about, so basically we talked about this, but in your opinion, is that a good strategy? Is protecting land a good strategy for protecting the Edwards Aquifer?
I was on the team that developed the model of identifying which pieces of property should be targeted for acquisition. I think it's a brilliant idea because ultimately there are limits to what the law can do, to what groundwater state regulations can do in terms of what you can and cannot do with your land.
Yeah.
And so while I'm saying stay off the recharge zone, don't do this, don't do that, to some degree it's idealistic.
Yeah.
There are limits, but you buy it, it's yours. You can say, I'm buying it and I'm putting these deed restrictions. It will never see X, Y, and Z sort of activities on that land. I think that's brilliant. And one of the challenges with that program has been finding the balance between volume of land, acreage, and the amount of money you have. Because there's land here in Bexar County, in the urban areas, that really needs to be bought and protected, but it's just too expensive. So a lot of land is being purchased to the west of us, Medina, Uvalde counties, which is great because that's helping preserve that clean volume of water to give us the dilution that we need here. So I think it's an excellent program. I hope it continues. I hope it continues to get funded. I've used San Antonio as a shining example in giving lectures around the world, saying here's a community that taxed themselves because they realize the importance of their aquifer to keep it clean. And of course, for those who aren't familiar, I hope most people are, that not all the money went toward aquifer protection. Some of it went to create these linear parks, these greenways that we now have, these beautiful hike and bike trails going north-south, throughout the city. So it's created a variety of parks, Crown Ridge Canyon, many others, expansion of Government Canyon, state natural areas. So there's a lot of stuff that's being done. I know they just added, but what was another 600 acres to Government Canyon. So it's great, it's protecting more of that watershed, more of the recharge zone.
Thinking about, unfortunately, the city doesn't have unlimited resources to buy the entire recharge zone. So decisions have to be made between different parcels of land. Do you have any takes on what method, you would use to determine the triage of how to grade one piece of property versus another if you had to choose between two? What can help determine which land is the most important to protect?
This was part of the model that we developed. We looked at the geology itself, knowing that some areas, some sections of the rock recharge more readily than others. We looked at the known karst recharge features. A common mistake people make is they focus on protecting recharge features and not the area away from the recharge features. The entire recharge zone is a recharge feature. Yeah. That's why it's the recharge zone. The entire area is vulnerable. But we looked at recharge zone features. We looked at drainage, because the more area of drainage you can protect that's clean, then the more effective you're going to be, the more bang for your buck you're going to get. We looked at adjacency, which is a factor of if your property is adjacent to a protected property, then that expands that drainage area that's being protected. So we looked at that. We also looked at factors like endangered species, because we do have several endangered species in the area. And so if I've got two properties and they're pretty much about the same, but on one of them we have an endangered species, well, let's take care of that. So we're getting more bang for the buck in that regard. So that's what the model does. And I would, I would encourage more of these bond packages to go through to buy as much of the property, as much of the recharge zone as possible.
Well, George, we talked about a lot of things. I could keep going, but I think we can end it there. I want to thank you again for talking with me. That was a really fascinating conversation. I really appreciate your time, and so thank you very much.
I'm glad to do it. Thank you. Thank you for doing this whole project.
My pleasure.
Thank you for tuning into this episode of the Recharge Zone podcast. Have questions, ideas for topics, or things you would like to share with us? Well, reach out to us by emailing us at rechargezone@edwardsaquifer.org. And be sure to subscribe to our podcast so you can have our next episode delivered right to you.